Hi there, I'm Chao from Zhejiang University, China. I'm going to introduce our work, which is named as Revisiting Supervised and Unsupervised Methods for Effort-Aware Cross-Project Defect Prediction. The information of authors are listed as following. My report includes 5 aspects. That is the background of work, the limitation in previous work, the details of our proposed method, the setting in our experiment, and the final results we obtained. First, I will introduce the background of work. Cross-project defect prediction has been an active research topic in software engineering, which aims to apply defect prediction models built on source project to a target project. Right now, a variety of supervised CBDP methods and some simple unsupervised CBDP methods have been proposed. In a recent study, Zhou et al. Found that simple unsupervised methods, for example, manual down and manual up, have a prediction performance comparable or even superior to complexity supervised CBDP methods. Therefore, this suggested that the manual down should be treated as the baseline when considering non-effort-aware performance methods, and the manual up should be treated as the baseline when considering effort-aware performance measures in future CBDP studies. However, there are a few limitations in their work. First, Zhou et al. Did not re-implement the baseline CBDP methods and just reported the baseline methods performance values published in corresponding original papers. Researchers may conduct experiments with different default experimental settings, which may result in unfair comparisons and consequently draw unreliable conclusions. For example, some work are conducted by Java language and some work are conducted by MATLAB language. All of them are treated as a partial baseline method in Zhou et al. Work. However, Zhou et al. Concluded their own experiment by R programming language. Second, different performance measures have been used to investigate the effectiveness of different CBDP methods. In particular, although Zhou et al. Discussed a large number of performance measures in their work, they only use a small subset of them in a specific comparison between supervised and unsupervised methods. For example, some work just reported AUC measure and some work just reported G1 measure. Therefore, Zhou et al. Only compared with this work in terms of AUC and G1. They did not compare with these methods in terms of any other performance measures. Limited performance measures can barely provide a holistic comparison of these methods' ability in CBDP scenario. Third, newly proposed effort-aware performance measures such as IFA has not been considered. These measures consider context switches and the developer fatigue due to initial false alarms. Since the limitation of testing resource and the impact on developers cannot be ignored in practice, their comparison should take these measures into consideration. Considering these limitations and yet the high impact of Zhou et al.'s work, we want to revisit their work by considering the same experimental settings and a more comprehensive set of performance measures. We first proposed an improved and a two-phase method named EASC, which is short for Effort-Aware Supervised Cross-Project Defect Prediction. The technical details of EASC are presented in Algorithm 1 and 2. As for the settings, we firstly consider 6 baseline methods. 4 methods are supervised ones and 2 methods are unsupervised ones. We totally consider 11 performance measures. These measures are grouped into 2 groups, non-effort-aware performance measures and effort-aware performance measures. In our experimental studies, we evaluate CBDP methods on 4 publicly available datasets, AAEM, NASA, PROMIS, and RELINK. These datasets are widely used in previous work. Our study explores the following research questions. Q1 is that what are the performance differences between the supervised and unsupervised method when different types of performance measures are considered? In the work of Zhou et al., they compared the performance of state-of-the-art supervised methods proposed for the CBDP scenario and 2 novel unsupervised methods proposed by themselves. They conclude that the simple model size methods have a prediction performance comparable or even superior to most of the existing CPDP methods, including many newly proposed models. However, there are a few limitations in Zhou et al.'s work. Considering these limitations, we want to conduct a comprehensive comparison between supervised and unsupervised methods using the same experimental setting and the same performance measures. To answer these research questions, we investigate two specific sub-questions. The question 1 is, what is the performance difference between supervised and unsupervised method? The question 2 is, what is the relationship between the inspection effort and the incident quantity? In question 1, we replicate the comparison between state-of-the-art supervised CPDP methods and unsupervised CPDP methods recently proposed by Zhou et al. To avoid implementation errors and make the comparison fair, we comprehensively use a Crosspair, a tool for benchmarking CPDP. Since it has implemented a larger number of CPDP methods and provided a full analysis in terms of different performance measures. Besides, based on this tool, we also implement ESC manual down and manual up. In question 2, we explore the characteristics of dataset in each project. We want to explore how unsupervised methods, for example manual down and manual up, perform on the full dataset, and analysis why or why not unsupervised method outperforms the supervised methods. Based on our intuition, larger instances have higher possibility to be defective. Therefore, we want to analyze the relationship between instance inspection effort, for example LOC, and the instance quantities. We sort instance of each project in descending or ascending order of the inspection effort, and want to figure out whether unsupervised method requires developer to inspect more instances. RQ2 is that could the supervised method be enhanced by leveraging the intuition of unsupervised method. We think that labeled data can provide useful information for building a high-quality model, and previous supervised works have made great progress in the CPDP scenario. Besides, inspired by Zhou et al., we should consider different methods for different scenarios. When the inspection costs are unlimited, we should first consider a larger instance, since as the previous study reports that larger instance tends to have more defects. However, in practice, we cannot ignore the limitation of inspection effort, context switches, and developer fatigue due to initial false alarms. Therefore, when the inspection costs are limited, we should first inspect the instance with a larger ratio between each instance defect prone and its inspection effort. Since the recent study argues that a smaller instance is proportionally more defect prone and hence should be inspected first. Here we list the results we obtained in our work. As for the question 1, we obtained that when considering NPMS, the unsupervised CPDP method manual down performs significantly better than supervised methods on most performance measures, for example F1 score and AUC, at the cost of higher inspection effort and higher false alarms. When considering EPMS, the supervised CPDP method perform significantly better than the unsupervised method manual up on IFA and PII et al. However, supervised CPDP methods perform significantly worse than the unsupervised method manual down on cost effort et al. And POPT. As for the results of question 2, we find that unsupervised method manual down obtains better performance at the cost of a higher inspection effort. As for RQ2, we make a comparison between ESC and unsupervised method. We found that when considering NPMS, ESC and Nantong have comparable performance, and the difference between the two methods are not statistically significant. When considering EPMS, ESC can significantly outperform Nantong with a larger improvement with respect to Cliff's delta in most cases. That's all. Thank you.
Okay. So, hello everyone, and welcome to this session and the first paper on revisiting supervised and unsupervised methods for effort-aware cross-project defect prediction. And I'm happy to have Chao, one of the authors here with us. And I see there are some questions from Jean-Louis Fan. Thank you very much. So we'll start with the first one. So how does your effort-aware method EASC calculate the two types of performance measures? Does it have different strategies for this? So.
Okay. Yes, I think our paper provides the EASC for supervised cross-project defect prediction. EASC has a different strategy to calculate the different types of performance measures. In particular, in our method, EASC is inspired by Zhou et al. In their work, they proposed two sorting strategies for different usages. That is the effort-aware setting and the non-effort-aware setting. So we bring them their advantages in our method for the two different settings. We use different sorting strategies. In particular, for the effort-aware setting, EASC first sort the testing dataset by the ratio between the score and the LOC in descending order. For another setting, that is the non-effort-aware setting, our method EASC sorts the testing data by the product of score and LOC in descending order. In which the score is the probability outputted by the classifier, and the LOC is treated as the proxy of inspection effort for the specific testing instance.
Okay, yeah. Thank you. And the next question is how do you split in the training and test set among the data sets?
Oh, okay. In our work, we use the dataset shared by the Herbert et al. That is for the four widely used dataset, NASA, IEEE, Relink, and the Promise. These datasets are also used the work in Zhou et al. Besides, for the project in one dataset, we remove this project that do not have the required minimal number of instances. In our paper, we use we treat the number as 5. This is the same setting followed by Herbert et al.'s work. Then each quantified project will be treated as a target project. Since our paper considering the static CPDP scenario, so the target project itself and any other version of the target project will be removed. For other projects left in the same dataset will be treated as the training dataset.
Okay, but does the dataset already come with a training and test set split, or how do you split them between training and testing?
Actually, we split the project as the testing date. So the left project in the same dataset will be treated as the training data. So the split is the same. We run our method for the same setting for about 100 times. Then we report the average performance.
Okay, I see. Thank you. So then we have a question from Aurora Ramirez about, I guess, in addition to supervised and unsupervised methods, you also have semi-supervised that tries to do some kind of hybridization between a supervised and an unsupervised method. So have you considered that? Because you do discuss how to do combining supervised and unsupervised methods in your paper. Do you know about semi-supervised methods?
Yeah, I know some about the semi-supervised method. However, in our work, our main goal is to revisit the work proposed by the Zhou et al. In their work, they only consider the cross-project defect prediction. They cannot put the semi-supervised method in their work, and they do not treat them as the baseline method. So in our work we do not consider the semi-supervised method.
Okay, but I mean, I think if I'm correct, you mentioned that one downside of the unsupervised was that there was quite some effort from someone, practitioners using the method. They would have to spend some effort in looking at the proposed, the predicted defective modules. So don't you think that some kind of semi-supervised method could help reduce some of that inspection cost?
Yeah, I think semi-supervised method can be can help the model to get the better performance.
And then
we can try it in the in the next work.
Okay, yes, future work, great. And then Aurora also answer questions a little bit. Can you really compare the unsupervised and supervised? I mean, they have quite different goals, I guess. Or do you see the last part of her question? I mean, the purpose is slightly different. She means that unsupervised is more about kind of understanding, analyzing, describing the data set in some sense. So.
Yeah, unsupervised, unsupervised are training with not the label of the date, but the supervised requires a large number of the labeled data set. I think this is the method provided by the machine automatic machine methods. In the scenario of the software defect prediction, researchers just use the method in our setting, and we want to compare the difference between the supervised and unsupervised. We don't know which one is the best one and is the most super method for our setting in the SDP scenario.
Yeah, but I guess, I mean, in general, there are many benefits if you can use more unsupervised methods, right? Because you don't need all of this labeled data. So for new projects, there could be many benefits, I guess.
Yeah, I agree.
Yes. So yeah, very interesting work. I think there's too little work in software engineering on unsupervised methods. So this is definitely important, and I think we can investigate it for many other areas. So yeah, I think we're getting to the end here, and this Q&A will soon end. And if you stay in this session, you will see the next paper presentation coming up. So we thank Chao and the authors a lot. This was a TSE paper in the journal First Track, and the next one I think will be from one of EMS's paper. Thank you very much, Chao.
Okay, thank you. Bye.
Bye.